Hello, everyone. Welcome to User Space Summit. Today, the first talk would be, I'll take you through the story of system tuning for latency measurement. So this talk, me along with Dave, we are going to present. Okay, so the talk is about mainly to find a deterministic latency on desired workloads. So because having a deterministic latency is very important um, to find exact numbers on given workloads. So DPDK, any DPDK application can benefit by tuning a system and the platform. So there are various aspects that you need to consider for tuning a system in order to achieve the deterministic latency. Example, like you need to look into what are the DPDK PMD configuration and the platform and the bias settings, and how you can isolate the cores that are doing the packet processing, and some of the kernel configurations. And also the interrupt prediction is important in order to achieve the deterministic numbers. Also, there are some frequency transitions and turbo boost that you can or must look into while you plan latency measurement. Okay, so the key tools that are being used for this benchmarking of this latency measurements of DPDK basic forward applications and traffic generators. So moving to next slide. So the goal of this presentation is to show how we can achieve the latency, which is very undeterministic to a very deterministic numbers. So the main focus is to go from orange numbers to the yellow numbers. So from this to this. Okay. Yeah. So if you do not have a system tuned properly, it's very obvious that you get the numbers of the latency everywhere. So you will not have any clear idea what's happening on the system. Okay, so to go into this settings, so let's start with the platform configuration that you should be doing. So to benchmark the latency, we have used Intel Xeon 6230 and CPU 40 gigabit Ethernet controller, and the software side DPDK basic forward application and the benchmarking code. So, and so there are, so if we start with the basic thing bias settings, so the things you need to consider are first goes with the turbo boost. The best is to disable this if you want a determinism, but you can have it enabled for your requirements, but you should take care of some good techniques where you can control the jitter because of a turbo boost, because the turbo can cause a frequency transitions. And the next would be the hyperthreading. So you make sure you disable if you're not using it, but if for the cases where you cannot avoid, you should make sure of techniques where the sibling threads cannot interfere with each other. Okay, there's other setting I would like to call out. CPU power and performance policy. It's better to set this to a performance. The other setting, like setting this to balance performance, what we observed was there was an increase in the value of the latency. So having this set to performance, there was a reduction in the latency value. So it's definitely recommended. Okay, so the key, there are, with respect to kernel boot parameters, there are few settings that you should do. So these are those settings. But we will try to cover these in the next slide. and we'll show how they impact the latency. Okay, so if you are running a DPDK application, make sure you are running a DPDK application alone on that core and nothing else. Okay. So let's see, to measure the impact of the mentioned configuration so far, as a simple approach, we used a benchmarking application, what this benchmarking application does is basically it runs a known workload of worth some 10 microseconds on our system. We run that workload for 1,000 runs. Each time, at each run, we record how long it took. So after 1,000 runs, we record min, max, and the average values. And we repeat this whole process for several times to collect the many samples so we can graph and show the impact of the settings. So the next slides that I'm going to show will have the latency numbers. So usually the things we should look for are called outliers. So any latency value which is higher than more than 1 microseconds from the average, at least on our benchmark application, is considered as an outlier. So any value within 1 microseconds from average is maximum and deterministic value. Okay, so this slide is about showing the latency impact of the ISL CPU, as you know, callback parameters and latency. So if you see the graph, it shows latency numbers. The y-axis showing a latency increase, and the x-axis shows the number of latency samples. Okay, so the yellow line is the latency achieved using benchmark when we have a system tuned with all the parameters. And the orange is numbers when we don't have these two parameters in our settings. So missing these parameters can cause and give outliers in the latency measurement, which will create confusion. So how they are going to impact these parameters, these two boot parameters, how they are going to impact, because one of these parameters, ISO CPUs, it basically disables the kernel from the scheduling algorithms. Hence, there will not be any kernel scheduling related interrupts coming to core. And also the other is, as you know, callback boot parameter, it disables no callback routines on that particular core. Hence, no interrupts, so we'll get the determinism. Okay, so the next slide. Yeah, this shows the impact of no heads full. So it is recommended to have this parameter in the boot parameters. So if you don't have this, you will see the periodic outliers in your measurements, and those are shown in the orange. Okay, so to make sure you avoid those outliers, you have to have this boot parameter, and for this parameter to work, you have to have a kernel which has a config no heads full enabled. So you look for kernel logs and see there's no log that you should see that this parameter is disabled. Okay. Yeah. And the next graph shows the impact of TSC boot parameter. The outliers with this are less, but they do appear at X seconds, whereas X is proportional to the number of cores that you have on the system. Okay, so better to get rid of them if you're doing really something serious latency measurements. Okay, so, yeah. Okay, apart from boot parameters, there are other settings that we would like to cover. Okay, the power settings, which is the first power setting that we are recommending is setting an Encore frequency to be fixed, because Encore frequency can cause frequency transitions if it is not fixed based on the workload and things. So that transitions again cause a jitter. So fix that frequency so it shouldn't get changed. So to do that, you can either set that using MSRs, or you can use a sysfs file system, which is available from kernel 5.6 and above. Okay, so yeah, it is most of the tuning techniques do suggest that we set the process, the work packet processing process priority to be high, if possible, and the scheduling to be FIFO or round robin. So try to set this to be high at least, so the workload gets a chance to run at maximum time. It will not get interrupted. So do that setting using a change root command. And the next would be a IRQ balancer. At least, to be honest, from at least on the system that we have done, we didn't see kind of advantage with this because we already had ISO CPU used. So, but it is recommended to disable IRQ balancer. Though if you have ISO CPU, just have this disabled to be more like sure. Okay, so there are usually interrupts are the main cause of the jitters on the cores. So to check what interrupts are coming on, what kind of kernel and NIC interrupts are coming onto your core, you can check them from proc interrupt file system. Okay, you need to keep monitoring them during your process benchmarking time. So you should see what is the trend of those interrupts and how do you minimize them. Okay, you can plan all that. So there is a simple script. This script, if you pass a specific code to the script, it will give what kind of non-zero interrupts are coming onto the code. So you can easily debug. Okay. And there are NIC related interrupts that will be keep coming to the core if you have a NIC with a multi-queue support. So you need to monitor those interrupts as well. So you need to grep for receive transmit core ID. So you will see those interrupts. So you need to make sure you minimize those interrupts. So for that, you just keep the interrupt NICs at the ports which you are using for your application and unbind everything out of the kernel. Okay, so do that using the DPDK device bind script. The second method would be, if you want to have those NICs or ports, make sure you have enough number of queues that are required for your testing. So you can do that with using a etool command. Okay. Yeah. So this is a slide on I40E latency benchmarking. So if you are doing a latency benchmarking with I40 driver, you need to tweak one of the I40 driver settings, because what we observe is if you during RFC 254 latency measurement testing, the I40 driver with the basic forward, it was kind of showing the stable numbers of latency, but at the end, all of a sudden it spikes up and it shows maximum as a 2 is so big number, which is very much varied from the average. On the graph on the right side, you can see that happening. So orange is the average and the gray bar is very huge, which is a maximum latency. It's a very spike coming up there. That is because I40 driver usually waits for the packets before it flushing out. If it's not receiving the packets, usually at the end of the test, you will not have the packets because test was stopped. So it will be waiting for the packets before flushing out. So the wait by default is 32 microseconds, and that was causing a latency and hence the bigger latency number. So if you're doing latency measurement, remember with I40 driver, you set this macro to 0 microseconds. Okay, so then you will have the numbers very stable as in the graph on the right side. So gray and orange are closely. Yeah. So with that, I'll hand over to Dave. Dave, are you online?
If you can hear me, can you hear me?
Yeah, we can hear you. Okay.
Sorry. Thanks for covering the first couple of slides, Reshma. I literally was having a heart attack trying to get in there. I dropped off just at the beginning. Anyway, we have 3 minutes left. Frequency transition. Pop onto the next slide there, Reshma, and we'll have a look and see what we have. So we're going to talk a little bit about hardware P-state scaling. So when you're using P-states in whatever form, whether that's requesting P-states through change requests from your application, or whether it's in Turbo, due to the number of active cores changing, you will get frequency changes if they're enabled. The graph on the right shows, typically if you have 2 cores active, you get a high turbo boost. If you have many cores active, you get a less turbo boost. So that causes frequency changes if you have turbo boost enabled and you have different number of cores becoming active and so on. So in order to avoid jitter, you need to, put design patterns into your application to avoid this jitter. So, for example, increase the queue size to allow more packets to come in while your while your core is transitioning to the frequency, and then it picks up on what's in the queue. You can also set the core frequency to be one fixed value. Say set the min and max of a frequency of a core to be the same frequency. Say all core turbo. And then it won't turbo up above that, so that when more cores come active, it still stays at the same frequency. However, there's new technology coming to help improve this, and that was announced at Hot Chips there a couple of weeks ago. The Hot Chips 32, one of the big industry announcements. So this slide is taken from that. So we've introduced faster transition changes in the cores, so that they can change frequency faster. So one of the main changes on the left is a bit of blurb there about phase lock loops and so on, but in a nutshell, what we're looking at in the graph on the right hand side is a known, as Reshma described earlier, the benchmark that we're running, a micro benchmark to actually run a known workload on a given number of cycles, an unoptimized number of cycles, and we measure how long that takes. And if it takes longer than expected, we know there's jitter, we know something has interrupted it. So when we change frequency on previous gen chips, we were seeing this 10 microsecond, 12 microsecond transition time. So if our workload took, say, 10 microseconds, for example, we would see an additional 12 microseconds on top of that when we change frequency. But Reshma, if you just pop onto the next slide. So what we've done in the new version is that these spikes have disappeared down, because if you see in the blue dots show the next gen CPU where that transition spike has disappeared. So that's a fairly significant change in the way we manage frequency and transitions. There's also changes in there to do with faster reaction, but I don't have a slide on that. But the most important one here is the speed at which the frequency transition takes place is reduced from 12 microseconds down to under 1, close to 0. So, and the final slide, Reshma, if we can go on to that. So the result of that means that it opens up new scope for transitions in DPDK. So applications that previously didn't do anything with power management, they can actually request frequency changes now, knowing that their frequency transitions is going to maintain the determinism of latency. Whatever latency they had previously, you can now frequency change while maintaining that latency, or having very little effect on that latency. It also means you can enable turbo, because of the fact that previously, if your workload was being transitioned due to other cores coming active, you might get throttled down depending on the number of cores and causing a frequency change. Now that impact is minimized. Any use case that avoided frequency transitions, basically, you could now go back to them and see, can we enable power management in those applications without adding the design pattern changes that you used to need in there. So this hardware change is fairly significant. So I'll read the last bullet there. DPDK users can now get more performance and save power while maintaining deterministic latency. That's the plan with the new change in hardware. So I think that's about all we have for you. Credits there to Chris Mack, who helped us a lot with the information, and Nilanjan, who allowed us to use the slides from the Hot Chips presentation. And I think we're about 1 minute over, but do we have time, Kevin, for any questions?
Yeah, so I guess the next session is starting now. We just started, so if people want to go to that, they can click on the sessions button and go to the next presentation. But I guess people can also stay here for a few minutes if there's questions. they can fire away.
Okay, see, the thing is, the next session is to do with latency as well, and I want to go to it. but anyway, let's see if there's any questions that we can handle. Otherwise, we can meet afterwards or do the networking session afterwards. So anyway.
Yeah, I mean, there's a latency room as well, so
yeah,
I mean, people can head over there maybe after the next session.
Pop in there actually into the latency room after the current talk that's on, and maybe we could answer questions there. And there's lots of really good stuff happening in the chat window that I'd really like to follow up on about iSalt CPUs and CPU sets and all of that. And it was just going up so quick I wasn't able to follow it all because I was trying to focus on the presentation. But yeah, lots of chat on this, so really good.
Okay, so I guess we maybe take the questions in the latency room, seeing as there's another latency talk on.
Sure.
So just thanks to David and Reshma for your talk. Thank you.
Reshma for handling the start of it. Thanks. Sorry about the technical difficulties. Slower in replay, Thomas. That's a good one. Yeah, thanks. All right, we'll see you in the other session.